So determine the components of a single couple equivalent to the two couples that you saw. So you have this 20-pound couple over here, and you've got this 30-pound couple over here. So you're asked to find the components of a single couple equivalent to the two couples that are shown. And you can do this choosing about any arbitrary point, right? What would be the easiest way to go about this? Where is it? Right here.
Would it be A?
Yeah, it would be A, right? Or actually, no, there's one even easier than that. Which point has the most forces on it? D, right? So you'll preclude the forces that you're acting about D, right? So let's find the moment about D, right? To work that out, say moment about point D is equal to, all right, so now you have, let's define our coordinate system first. So you have, it's already defined for us, sorry. X, Y, and Z is in this direction, right? So moment about D, it's going to be this 30-pound force, right? And it's going to be R from D to C, right? So what's that position vector going to be? It's going to be 9 plus 9 in the positive Y direction, right? So, you know, I'm doing gallery view on Zoom, and I'm curious to see how that comes out on the recording because I've never done that. Is it just going to be the whole thing and my screen? You won't be able to see it?
Yeah, it's just the entire PowerPoint screen.
Okay, but then what about, usually there's a small window, right? Or that doesn't show up with the speakers?
Nope.
All right, good. I'll hold you to that. All right, so then you have your R for this 30-pound force, which is 18 inches in the positive Y direction. So you have 18 inches J hat. So that's the first term, crossed with 30 pounds, and that is acting in the negative Z direction, right? So it's in the negative Z. So positive Z is this way. So 30 pounds is in the negative Z. So minus 30 K hat, right? And let's just stick with our units so that we're good. So 18 inches, and then this is in 30 pounds over here, plus this other force of 20 pounds, right? So the position vector of point E with respect to D is you have to go 9 inches in the positive Y direction. So you'll go 9 J hat, again in inches, plus you go 12 inches in the negative Z direction. So negative 12 K hat, right? And then running out of brackets. See that master bracket like that. So that one crossed with your 20-pound force, which is in the negative X, right? So you have minus 20. This is pounds in the I hat direction. All right. Again, you can do it in Mathematica, you can do it by hand, you can do it on your calculator. I'll just give you guys what I have the final answer, and you can check that out when you're doing your revision. So what I get is at the moment is equal to minus 540 I hat plus 240 J hat plus 180 K hat, right? And that is going to be in pound inches. All right. So that's the equivalent moment for all of these couple moments. Good? Any questions? No? Okay. So let's go on to the next question. So you have a fixed crane that has a mass of 1,000 kgs and is used to lift. You know what? I don't think we're going to have enough time to do the last one. So let's do the last one first. You'll get the solutions for this one, don't worry. And this one is in 3D. So a sign of uniform density weighs 270 pounds. So this guy weighs 270 pounds and is supported by a ball and socket joint at A. So it's free to rotate about there, only reaction forces, no moments, and by 2 cables, right? So you're asked to find the tension in each cable and the reaction at point A. All right. So let's start off by doing what we do best, drawing the free body diagram, right? So when we're looking at the free body diagram, right, let's go first. So first we'll have the weight, which is going to act at the center, right? So this acts downwards, and with the coordinate system that's been defined for us, y, x, and z, like that, you can say that this weight W is equal to minus 270 pounds. Whoops. So it's in the negative y direction, so minus, and you get j hat, right? What else? So I have a tension in this cable, right? Always in tension. Tension from a point is always acting away, right? So you have T, BD, like that, right? And because you're telling the direction, let's just keep it as a scalar, right? Then you have from point E to C, right? Again, this will be in tension. So you'll have another force like that. So let's say that that is T, EC, that way, right? Then what else? What am I missing to solve the problem? Let's go back to the problem statement. So all it was asking us for was the tension in each cable and the reaction at A, right? So what am I missing? I'm missing my reaction, unknown reaction forces at A. So as we said, the unknowns make our lives easy. Define them in the positive directions, right? So AY, AX, and AZ. All right, and I'll use a mix of hand calculations and Mathematica to do this because it's good practice to do the stuff beforehand, right? So now the next step is to write out your unknown forces as vectors, right? So my force A unknown is just AXI plus AYJ plus AZK, right? Make sense? Okay, then for TBD as a vector, right? So it's going to be, and we go back to defining our unit vectors, right? So it's going to be the scalar quantity TBD times the unit vector from the direction vector from going from point B to point D, right? And we know that the unit vector is nothing but the position vector, working about the origin. So RD minus RB divided by the magnitude of RD minus RB. Right? So that becomes equal to TBD, and RD is equal to, where is D? RD is equal to, you have 8 in the negative K, right? And you have 4 feet in the positive Y. Minus, then you have RB, which is just 8 feet in the positive X, right? So minus 8 I hat, right? And divided by the magnitude. It's already in I, J, and K for us. Life has been made easy, right? If you figure out what the magnitude is, I'll let you guys do the math, or do you want me to write it out? Or can I just write it out straight away? Make life easy. You know what? Never take shortcuts. That's what, although engineers love taking shortcuts, so I'm kind of ambivalent about that. So 8 square plus 4 square plus 8 square. The innovative engineers all take shortcuts. That's where the innovation comes from. All right, so we are at inches below, inches above. I'm not going to write that out. TBD is unknown. This becomes equal to 12, if I'm not wrong, right? You guys figure that out?
Yep, that's good.
All right, so then if we write it out, we get TBD times minus 2 over 3 I hat plus 1 over 3 J hat minus 2 over 3 K hat. All right. And similarly, oh, one thing we forgot to do in our free body diagram was that obviously that is going to equal, 8 feet divided by 2, and that distance is going to equal 4 feet as well. Forgot to mention that. All right. Then doing the same thing for TEC, right? That's going to equal TEC times the unit vector going from E to C, right? So that's going to be equal to RC minus RE divided by the magnitude of RC minus RE, like that over there. I'm not going to work this one out. We're all grown-ups here in terms of what statics is. So just writing out what the final thing comes out to be. So that's just TEC times minus 6 over 7 I hat plus 3 over 7 J hat plus 2 over 7 K hat. All right. And I believe the problem has been set up for us, right? Because now this is where the beauty of Mathematica lies. You can just simply say that your sum of forces is equal to your complete force vector A plus your complete force vector TBD plus your complete force vector TEC plus your weight vector, and that is just equal to 0, right? And then Mathematica will be able to individually figure out the 3 equations, what they're going to be, right? And then again, for your moment equations, you take moments about the point A, right? So when you're taking moments about the point A, the only forces that you have to worry about are TEC times TBD, no, not times, TEC, TBD, and the weight W, right? So that moment is just going to equal, let's say, R of, what do we call it? From E to A crossed with TEC as a vector plus R from B to A crossed with T, what was it, TBD, right? Plus, let's say that that point is also, we just call it W. So R of W to A crossed with your weight vector W, and that guy is just equal to 0, right? Now, REA, we know. RBA, we also know. RWA, right? We know in the I hat direction, it's how much? 4 feet, right? So that's 4 feet in the I hat direction. What is it in the J direction? It's just 5 over 2, but you're going in the minus J direction, right? So minus 2.5 feet j hat. All right. Everything else we've already worked with before.
So when inputting into Mathematica, you would define all of the terms and then you would just put in the force equation and the moment equation.
I'm going to show you that.
Okay.
So now when you're inputting into, oh, I apologize. I kept the text really small. So let's make it bigger so that you guys can see it. All right. All right, you guys will help me out with this one because, well, it's difficult doing split screen for some reason. Oh, maybe not. There we go. All right. So what do we call this? We say that this was problem 3 from, and I'm terrible at commenting, so I apologize for you beforehand, right? In the programmer's world, if you're terrible at commenting, that's great, right? Because what that means is job security, because no one else can read your code. So problem 3 from week 1, class 2. All right. So then we have freeform input. All right. Oh, no, not that. Just press the plus sign. There we go. All right. Freeform language input. So now let's define what our unknown. So our unknown A is just going to equal now the individual unknown parts, right? So you have AX in the I hat, AY in the J hat, and AZ in the K hat, right? So that one is done. Then you have, let's do TBD, right? So what was TBD equal to? TBD was equal to your, let's say, the unknown scalar quantity TBD, and you multiply that by your unit vector direction, which was just minus 2/3 in the I hat. Then it was, and I'm excessive with my parentheses, so you don't need to do that, but this just helps me in debugging, right? So 1/3 in the J hat direction, and then you have minus 2/3 in your K hat direction, right? So that defines your TBD. This small, I didn't, you get into redundancies when you start using the same variable names inside and outside. Just stay away from that and keep it different. That just makes life easier. Because Mathematica doesn't know the difference between a scalar variable and a vector variable, and it'll get all confused on you. So just keep them separate. So then you have TEC, which is equal to your scalar quantity TEC times, now I have minus 6/7, comma, also my J hat is 3/7, and then my K hat is 2/7. Whoops, I'm gonna mess up. All right, there we go, like that. Then our weight vector was just minus 270 pounds in the negative J hat direction, right? So 0, minus 270, 0. So there you go. That's your weight vector. Weight vector. All right. What else do we need to define? We need to define, let's do REA. So REA is equal to, REA is just 6 feet in the positive X direction, right? So it's just going to be 6 inches. 0, and also Mathematica is obviously doesn't know what units you're talking about, right? So it's up to you to be consistent and stay consistent with your units throughout. All right, and then you have our DA, which is what? Which is just 8 feet in the positive X direction, right? So that's just going to be 8 times 0 times 0. Oops, didn't want to do that. Small r there. All right. Then we have our WA, which, what did we say it was? It was 4 feet in the I hat direction and minus 2.5 feet in the J hat direction, and nothing in the K, right? So that's our WA. And that's it. Now you're ready to solve. So you open up your solve expression. And the way that you solve simultaneous equations in Mathematica is, let's write out the complete thing for you guys. So you have to put the function square brackets, and then you have to define 2 curly brackets inside. In the first set of curly brackets, you define what your expressions are that you're solving. In the second curly brackets, you define the unknowns that you want Mathematica to solve for in the expressions that are there in your first curly bracket. So here we just have our force equation and our moment equation, right? And the beauty with Mathematica is that you can just write out your 3D equation as one and your all your 3D equations as one, and then just specify what variables that you're solving for, right? So here, what's my first expression? My first expression is that this vector A plus the vector TBD plus the vector TEC, and this is all the vectors that we defined up above, right? Plus the vector W is equal to 0. Now, with coding, usually when you have 1 equal to sign, that means that you're forcing stuff to be equal to there. But when you're writing an expression and you're saying that it's equal to 0, you have to use equal to equal to. I forgot what the exact verbiage for that is, but you have to use equal to when you're writing these expressions that you're solving for. All right, so that's your first equation. And then the way that you separate equations is just by using a comma, right? And then my last equation is what? I've got 3 cross products. So I've got cross of REA times TEC plus cross of RBA and TBD plus cross of RWA and W, right? This is also equal to 0. So now I've defined all my expressions, right? And what are my unknowns? My unknowns, Mathematica makes life easy. The scalars on top is just these 5 guys here. So you have AX, AY, AZ, TBD, and TEC. Whoops, TEC like that, right? You do your prayer, cell prayer, please make this work. Hit Shift Enter. There you go. It worked out all right. Because you defined a decimal here, it ended up solving everything numerically, but typically it would have solved it as a fraction, but it gave you, it found these exact answers. All right, so what does that mean? That means now we can say that our unknown TBD was equal to 101.25 pounds. My unknown TEC was equal to 315 pounds. And then my force vector A was just equal to 337.5 I hat plus 101.25 J hat plus, oops, sorry, minus 22.5 K hat pounds. All right, good stuff, easy peasy. Any questions? Mathematica is going to make our life very easy. We're going to be doing a lot of cross products and stuff like that as we go forward, especially when we move on to the later second half of the course, when we do rigid body stuff and everything is just insane at that point. So yeah. Good. Any questions? All right, thanks guys. I'll see you all on Tuesday. We'll finish up statics on Tuesday, and that'll be your first homework, will be the static review stuff.
Concerning the software to use for solving,